triangles and their properties, triangle areas, special triangles, similar congruent triangles, triangle centers, a very basic introduction to trigonometry, and some practice questions we'll go over together. So triangles and their properties. So if you don't know what a triangle is, I think you're in the wrong class, but so it's the most basic polygon within Euclidean geometry, and they can be classified into 6 different categories: 3 by their angles and 3 by their side lengths. So what are the categories? The angle categories are acute triangles, which are basically triangles with degrees all less than 90. And then we have obtuse triangles, which are triangles with at least, well, exactly one obtuse angle, which means that angles are, yeah, the angle is greater than 90 degrees. And there can only be one obtuse angle because the sum of the degrees in a triangle is 180. So if you have one that is greater than an angle that is greater than 90, the rest must be less than 90. So yeah. And then we have right triangles. There's only one right triangle. Same logic with obtuse angles. There can only be one right angle. So that answers that question. We have equilateral triangles, which are triangles with sides of all equal length. We have isosceles triangles, scaling triangles. Isosceles triangles, they are triangles with at least 2 sides of equal, or that are equal in length. And then we have scaling triangles, which have sides that are all different lengths. So like an example of scaling triangle would be like, let's see. So like if we have a 3, 4, 5 triangle, everyone knows that that's a scaling right triangle. You can classify one as an angle and then one through the lengths. And if we have like a triangle with side lengths 3, 4, and 4, then that is a I think it's, yeah, so it'll be an acute isosceles triangle. So you can identify triangles using these 6 categories. Okay. Wait. Okay, now we're on to triangle areas. Okay, onto triangle areas. A new person, yay. So we have, so we have a bunch of formulas for the area of a triangle where, and in this case, A is referred to the area of the triangle. So we have base times height, which most of the times if you have a known base and a known height, so you always know the area. But there's some cases where, let's say you have a unknown height, and let's say that's what you're trying to solve for, you can use that with a known base to maybe like find stuff. You have the incenter, which is denoted as R, or lowercase r, because the circumradius is denoted as capital R, and a semiperimeter S, and it is known that in radius times the semiperimeter is also the area. And then we have Heron's formula, which takes the same semiperimeter concept, and we get this formula, which the product of the sides divided by 4 times the circumradius is the area. Most of the time you won't see this be used for area. Most of the time it'll be used for like finding the circumradius, because this is like one of the few formulas it shows up in, as well as the extended law of sines. That's kind of more advanced. So if you know trig, you can also find the area is 1/2 times 8 times the product of 2 sides times the sine of the angle made by the two sides. And yeah, so see why so one I guess this diagram shows neatly how this formula, um, this one is true. That's terrible. But basically you can see in the diagram, we can connect um, the altitudes, or we can drop the altitudes of each sub-triangle like this. This triangle is one, and then we have other triangles. There's two other triangles, and if this is the radius, then we know that this and the area of this triangle is this side B, B times R over 2. So it's B times R over 2. So BR over 2 plus, and then we have the same thing with other logical triangles, I guess. AR over 2. And because this is R times A plus B plus C over 2, we get R times the semi-perimeter is also the area. That's not what I want. That's not what I want either. I'm not sure how to erase very fast on this, so please bear with me as I slowly erase my drawings. Well, so yeah, that's how the derivation of the semi-perimeter 10 degrees from the works. There's another person. Yay. Okay, we can deal with a bunch of red dots. Okay, so I'm just going to continue because I don't care about the red dots. So, they go away. Okay, special triangles. So we'll start with 30, 60, 90 triangles and 45, 45, 90 triangles. So they're referred to as 30, 60, 90 triangles because those are the measures of the angles in the triangle. It is good to know the ratios of the side lengths. The hypotenuse has a 2-to-1 ratio with the smaller leg, as you can see here. And the larger leg has a 3-to-1 ratio with the smaller leg. And this is obviously some Pythagorean theorem. We'll get to that later. And then we have the 45, 45, 90 triangle, also referred to the angles of measure the angles in the triangle. That's how the name comes. And the two legs are of equal lengths. That's why this one is pretty important. And also the ratio between the hypotenuse and the leg is √2. It should be √2 to 1. Yeah. So that's really what. So these are, I guess these come up quite often. I think the 30, 60, 90 triangle comes up whenever you're talking about either equilateral triangles, hexagons, or anything, any shape or regular polygon with a side length that is a factor of 3 or 6. Usually 6, but equilateral also uses these. So there's also 45, 45, 90 triangles. They show up, I guess, in octagons, I think. Yeah. So if you have an octagon problem, it may be helpful to draw so you have an octagon. Okay, I'm just gonna write in the middle of the screen. if you have an octagon and you can write or complete the square around it, right? So now you have a square with like these these lengths drawn, and this area here is the octagon, right? So and we know that because of the angle of the interior angle of an octagon is 135. That means this is a 45, 45, and this is right. So this triangle here, this triangle here, this triangle here, this triangle here are all 45, 45, 90. So you can use these 1 and 2 here. Pretty find some stuff, I guess. Um, kind of don't want to erase everything again because I don't know how to erase fast. But so I'll just go to the next one and they all disappear. Okay. So right angle triangles. So this is where the Pythagorean theorem shows up. It relates the two legs with the hypotenuse. Given legs of length a and b, the length of the hypotenuse is square root of a squared plus b squared. In other words, yeah, it's c squared equals a squared plus b squared. Everyone in middle school should know this theorem, or everyone in middle school know. This is like pretty fundamental, I think one of the first things you learn when you get into competition math. Yeah, there are there's like millions of proofs, so I'm not gonna go over one. You can probably go find one yourself. You can probably derive it yourself, actually. So that can be something you do in your free time. And we also have the geometric mean theorem. The geometric mean theorem states that the square root of this and multiplied by that, or x times y, equals h squared, or in other words, square root of xy equals h. You can solve this or prove this using ratios in similar triangles, but that's something else. I might go back to this slide because we also have a similar triangle slide. Okay, so I also have a practice problem, I guess. In quadrilateral ABCD, angle B is a right angle, diagonal AC is perpendicular to CD, AB is 18, BC is 12, and CD is 14. And your job is to find the perimeter of ABCD. So I'll set time for like 3 minutes, or maybe it depends on how many people send me the answers. So yeah, I'll give you some time to do this starting now. Okay, I've gotten a few summations, so I guess I'll go over the practice problem. So basically, from the practice problem or from the problem statement, you can see that we can construct A, B, C because they're connected. A, B is a right angle. You have A and C, right? And given that diagonal AC is perpendicular to CD, right? So let's say D is over here. That means this is a right angle because that's the definition of perpendicular. AB is 18, BC is 21, and CD is 14. So you can use Pythagorean theorem twice. You can use it to find AC, which I guess is the square root of this 18 squared plus 21 squared. And I know 18 squared is 324, 21 is 441. So it is the square root of the sum of this. So AC is the square root of this, right? And since I use Pythagorean theorem again, I don't need to worry about the square root because that's how, but it goes away when I square it. You just need to add 14 squared to find AD squared. So I know 14 is squared is 196. I add this up. One. Wait, am I bad at math? No. Okay. 4, 2, 6, 5, 15. And then you do more math. Yeah. Just be 6. Yeah. 961. And you notice, so that means that 80 is root 961. So 961 just happens to be a perfect square. It's 31 squared. So 31. So because it asks for the perimeter, we have 31 plus 18 plus 21 plus 14 equals 084. I put an 0 at the bottom because this is actually from Amy. So if you got it, you just did an Amy problem. Yay. Are there any questions? Okay, I'll just move on. Okay, so we have more special triangles, and we're starting with equilateral triangles. So an equilateral triangle is a triangle that has all the lengths of equal measure. So like, yeah, I guess that's pretty self-explanatory for equilateral. You can find the root word equal in it. So all the sides have equal length, and all the angles are 60 degrees. And one idea, as I mentioned earlier, that 30, 60, 90s triangles come in, they come in every single equilateral triangle. Because if I have an equilateral triangle, I can split it down the middle. So this is 30, this is 60, this is 90 degree. So this is X. This side is also X. Yeah, and you can solve for stuff. And then we also have isosceles triangles. And isosceles triangle, I'm sure you already know. But the base angles, that's not a good spot. So the base angles like this and this, they are equal if these two are equal, which is the definition of an isosceles triangle. And an idea for isosceles triangle is dropping the altitude. That's terrible. This is always going to be right, and this is always going to be a median because it's isosceles. You can prove this using, or show this really using some similarity and congruence formulas. So, and that's what we're on to next. So similarity theorems. I'm sure many of you have seen these. Maybe you haven't paid attention to them, but I guess they're pretty important. So similarity theorems. There are four, um, well, really three, but four because I included the fourth one. It's the same thing as, uh, wait, yeah, it's the same thing as two, really, because two angles. I'll just, okay. The first one, SSS, is side similarity, I guess. And I guess this diagram explains it pretty well. If AB, the ratio between each corresponding side is in an equivalent ratio all across the triangle, then they are similar. This is like saying a 3, 4, 5 triangle is similar to a 6, 8, 10 triangle. It's just a constant that you multiply the sides by. And then there's angle when two corresponding sides or two corresponding angles are of equal measure. Equal measure, not there's a ratio, but there's an equal measure. And this also implies that the third one is also equal because the sum of the degrees in triangle is 180 degrees. And then there's side angle side. If AB is similar to DE and AC is similar to DF, you can get that ABC is similar to DEF. Yeah, this is an important one that shows up quite a bit. And then there's angle side angle. This isn't really that important. It doesn't show up that much, but it's really just the second one plus the side. Because if you know two angles are equal, then you already know that they're similar. Oh wait, also this should be SSA. Warning. So SSA is not a similarity theorem. There's a funny quote, but that's not very appropriate. I'll send it in the Discord later. That helps you remind that this is not a similarity theorem. Uh, it's with Wolfram Alpha, my favorite. Okay. Similarity properties. So all the angles are the same, all the corresponding sides are in the same ratio, and the ratio of the area is the ratio of the side lengths, but squared. And other triangles can also be created, other similar triangles can be created through a dilation or any homothency. That's kind of Olympiad topics, but so these facts come up. So always look for these because similar and congruent triangles are like the heart of competition geometry. Okay, so I have two practice problems, and I'll give 5 minutes to do both, and then I'll probably hand it off to Tina to finish.
Okay. There's a lot of answers in the chat, so I guess I'll start explaining. In the first problem, we're finding BC and DC. The key step is to realize that BDC, triangle BDC, is similar to triangle ABD. Let me...
You want me to stop sharing?
Wait, Eric. Yeah, I think that would be good.
Okay.
Because I can't seem to annotate the screen. Okay. Can you see my screen now? While we're waiting for the slides to come up, the key step is to realize that, oh, here they are. That's good. Triangle BDC is similar to triangle ADB, which are 3, 4, 5 triangles. So if we set the ratios, 3 over 4 equals 4 over DC equals 5 over BC, we would get DC equals 16 over 3 and BC equals 20 over 3. And it's easy to see that it's easy to check because 4 it's just 12 over 3, and 12, 16, 20 is another version of the 3, 4, 5 triangle. Now let's move on to the second problem. We're trying to find ON and MN. We can easily see that OMN is similar to LMO, which is also a 3, 4, 5 triangle, because after you multiply everything by 10, it turns into 1.2, 1.6. The 1.2 turns into 12, the 1.6 turns into 16, and the 2 turns into 20, which is again 12, 16, 20. If we set up the ratio again, we would get 1.2 over 1.6 equals 1.6. 1.2 over 1.6 would equal 1.6 2.6 would equal 6 ON over 2, which equals MN over 1.2. Solving this, we should get 1, 2, ON equals 3 halves and OM equals and MN equals 0.9. And this, if we convert the 3 halves into decimals, we get 1.5, which shows that this is a 9, 12, 15 triangle, which is similar to a 3, 4, 5 triangle. Got it? Now, congruence. When two triangles are congruent, that means they're exactly the same. They might be rotated, but the side lengths and the angles are the same. The 5 main ways to determine if two triangles are congruent is first, SSS, which is when triangles have the same sides. Like a 3, 4, 5 triangle is always congruent to another 3, 4, 5 triangle. This is easy to see because congruent triangles are supposed to have the same sides. The second one, SAS, side angle side, which means when both triangles have two sides that are equal and the angle between is also equal. Let me draw this to show. So let's say I have a triangle that looks like this. I have another triangle that looks like this. If I know that this side equals this side, usually when we know side, if we mark sides with the same type of marking, like these two sides have 2 lines, that means the sides are the same. This side has 1 line, so these two sides are the same. And if these two angles are the same, then that means these two triangles are the same. And the symbol for congruent triangles is a curve above an equal sign, like that. The third one is ASA, which is a lot like SAS. It's when two triangles have the same 2 angles and the side between the angles are the same. I'll draw this again. So we have one triangle, we have another triangle. If we know that this angle and this angle are the same, and these 2 angles are the same, and the side between the 2 angles are the same, we know that they must be congruent. The fourth one is angle, angle, side. It's when there's 2 congruent angles and a side not between the angles is congruent. If I draw this, it would be like there's 2 triangles. We know that this angle is equal to this angle is equal to this angle. And if we know that this side is equal to this side, then we can also know that the triangles are congruent. The fifth theorem is mainly used with right triangles because they have congruent it's right triangles. If we know that these 2 triangles are right triangles, their hypotenuses are the same, and they have one leg that's the same, then they're also congruent. Because we can use Pythagorean theorem to find the other leg, and they're going to be the same. Just like with similarity, SSA is not a valid congruence theorem. And now let's move on to triangle centers. The first one is a circumcenter, which is the intersection of 3 perpendicular bisectors. And a perpendicular bisector is a perpendicular line that divides a segment into 2 equal parts. And you can see at this picture, J would be the circumcenter. IE is the perpendicular bisector of BC because BE equals EC and IEC is a right angle. The distance from the circumcenter to the 3 vertices is the same, and it is the circumradius. If we inscribe a circle around the triangle, the circumcenter is the center of the triangle. So you can see that BD is the circumradius, D is the circumcenter, and you can inscribe a circle around this triangle. The next center is the incenter, which is the intersection of three angle bisectors. Angle bisectors themselves have unique properties. First, they split an angle into two equal angles, like in this picture, BAD equals DAC. So AD is an angle bisector, and there's two theorems related to angle bisectors. The first one is from this picture, BD over DC equals AB over AC. There's variables in the diagram, but sometimes it's also written as AC over DC equals AB over BD. The second theorem is that to find the length of an angle bisector, AD in this case, AD squared equals AB times AC minus BD times DC. It's quite easy to remember. It's the product of the two actual sides minus the product of the two separated sides. The segments the angle bisector separates this side, BC. So there's BD and DC. Got it? A triangle has three angle bisectors, and just like the perpendicular bisectors, they intersect at one point, the incenter. In this case, in this picture over here, the incenter is I, CF, BD, and AE are the angle bisectors. One interesting property is that the incenter is the center of a circle inscribed around a triangle. If you remember from the perpendicular bisectors, if you inscribe a circle, if you draw a circle outside the triangle, then it circumscribes the triangle if it goes through all 3 points. The inscribed circle will be tangent to all 3 sides. An interesting property is that they are going this when you connect the tangent points to the radius, it will form right angles, like IHB is a right angle, IJC is a right angle, and IGC is a right angle. And another property of the tangents is that there's going to be a lot of congruent sides. So given a triangle, we can find the length of the in radius, which is the radius of the inscribed circle, like IH, and we can find the length of these tangent parts. Let me pull up. How about an example to make this clear? Let's say we have this standard 3, 3, 4, 5 triangle. And we inscribe a circle inside it. First, I would like you to find the in radius of this circle. And if you remember from the area slide, area equals semi-perimeter times in radius. And semi-perimeter is just half of the perimeter. And second, using the property that tangents are congruent, can you find the length of each of these tangents? I'll mark them off in variables. That's an A. I'm sorry, I just cannot write with a mouse. I'll give you 2 minutes and you can start. And remember, message the answers to, I would prefer you to message the answers to me.
The arsenals are so powerful that all-out global war could cause a nuclear winter.
I'm getting a lot of answers, so I'll go ahead and explain. So using the area formula, we can find that we know that the area is 6. The semi-perimeter is also 6. So the end radius is 1. And to find A, B, and C, we can set equations like A plus B equals 3, A plus C equals 5, and B plus C equals 4. So we get that A equals 2, B equals 1, and C equals 3. And it seems like everyone got that right. The third center is a centroid, which is the intersection of 3 medians. A median is a line segment from a vertex to a midpoint of the opposite side. In this diagram here, AM is a median of BC because BM equals MC, and the length of a median is this formula. 2 times AM squared equals AB squared plus AC squared minus BM squared minus MC squared. It's a little like the angle bisector formula, except that you have to multiply AM squared by 2. And it's the long sides, the sum of the long sides minus the sum of the cut sides. The centroid itself doesn't have a circle associated, but there's some useful properties, such as the distance from the centroid to the vertex is twice the distance from the centroid to the side, such like AG would equal 2 times GD, because G is the centroid here. And similarly, BG equals 2 times GF, and CG equals 2 times GE. And the medians also divide the triangle into 6 small triangles of equal area. So the 6 triangles you see here, I'm marking them right now. They all have the same area. The last center we're talking about today is the orthocenter, which is the intersection of the heights. The height is a perpendicular segment from the vertice to the opposite side. Like you can see in this picture here, the red lines are the heights. They intersect at the orthocenter, and they don't have a circle associated, but they also have properties because they make a lot of right angles. Another useful property is that you can circumscribe a circle around many quadrilaterals. We will talk about cyclic quadrilaterals in a later lesson. So given 3 non-collinear points, they form a triangle. And there's exactly 1 circle that goes around each triangle. But there are some quadrilaterals that can't be inscribed. Like you can inscribe a rectangle, but not some of like you can't inscribe this around a circle. And cyclic quadrilaterals themselves have many useful properties we'll talk about in a later lesson. The last section I'll talk about is basic trigonometry. So you probably seen or heard of this before. there's three main functions: sine, cosine, and tangent. So if we're talking about this angle theta over here, and this would be the hypotenuse, this would be the side opposite of it, and this would be the adjacent. So if this was the standard 3, 4, 5 triangle, then sine of theta would be 4/5. Usually trig doesn't come up in AMC 10s because it's more AMC 12 material. If you know trig, there are two important rules. There's the law of cosines, which looks a lot like the Pythagorean theorem. The special case for the Pythagorean theorem is when C equals 90 degrees. So you get rid of the 2ab cosine C term because cosine of 90 degrees is 0. But generally, if you don't have a right triangle, you can solve for a missing side given an angle and two sides. There's also the law of sines, which helps you find. There's also the law of sines, which helps you find missing angles or sides. And now for some practice questions. I'll let you try this for a minute or two, and I'll explain them.
Okay, so I guess I'll explain the problem now. I'll annotate here. Okay, so in a given plane, it was here. Okay. So in a given plane, points A and B are 10 units apart. So I have point A, B, right? And this is 10. So how many points are there C in the plane such that the perimeter of triangle ABC is 50 units and the area of a triangle ABC is 100 square units. So recall that the area is base times height, right? So if AB is my base, really, because C can be anywhere. C can be here, here, here. There will always be a height, right? Okay. So the perimeter. So because of this formula, I know that C is either because the area is 50 and the base is should be base over 2. The area is 50, so the perimeter is 50. Wait, no, the area is 100. Sorry, the area is 100. So, and I know the base is 10. So that means the height of wherever C is, let's say C is over here, then that means that this is 20. And then if C is down here, this is also 20. And note that perimeter, as Tina said in the hint, that perimeter is minimized when there's symmetry. So I know that it'll be on the perpendicular bisector because it has to be because it's the height, so it'll be a 90-degree. So I know this is 20, and I know this will be 5, because this is if I want to minimize the perimeter. And I know that each one of these is square root 425 by the Pythagorean theorem. But because the perimeter is 50 units, 45. Because the perimeter is 50 units, I know in this case the perimeter is square root 425 or 2 times square root 425 plus 10. But there's a contradiction here that this is greater than 50. Because we've already minimized perimeter, this is impossible. So there are 0 points in the plane such that this holds. Okay, so moving on, I guess.
All right. The second one is 2019 problem 15. Right triangles T1 and T2 have areas 1 and 2, respectively. A side of T1 is congruent to a side of T2, and a different side of T1 is congruent to a different side of T2. What is the square of the product of the other sides of T1 and T2? I'll give you a few minutes to think about it. Would you like more hints or would you like me to explain the problem? So far, I haven't received any answers yet. I guess I'll go ahead and explain. Like I've stated in my hints, first we need to figure out which sides are the congruent sides. We know that one triangle is bigger than the other, and so the two longest sides in the small triangle are going to be equal to the two smallest sides in the big triangle. Like I've noted here, there's A, which is the long leg of the small triangle and the short leg of the big triangle. And there's B, which is the hypotenuse of the small triangle and the long leg of the big triangle. Using the Pythagorean theorem, we can figure out that this short leg of the small triangle is going to be square root of b squared minus a squared, and the long leg, the hypotenuse of the big triangle, is going to be square root of a squared plus b squared. So what we're trying to find will be a difference of squares, which would eventually be square root of a squared plus b squared and b squared minus a squared. We square this, so we just get b to the fourth minus a to the fourth. We know that ab equals 4, and we know that ab equals 4, and square root of b squared minus a squared times a equals 2. So we get that a equals the fourth root of 12. So we know that a to the 4 equals 12, and b equals 4 over a, which means that b to the 4th equals 4 to the 4th over 12, which simplifies into 256 over 12. We take out the 4, that gives us 64 over 3. And 64 over 3 minus 12, which we can write as 36 over 3, eventually gives us 28 over 3. So this is the answer is 28 over 3. Do you understand that? Is there anything you would like me to go over again? Okay, I guess I'll move on. Now we're working on 2019 problem 16.
Okay, I'll explain this problem. So I need to annotate. So the problem states that we have a triangle ABC with a right angle at C. So I can draw this C, and I know the other one must be A and B. Actually, I should probably yeah, make that's not there. Or maybe it's okay. So, and I given that point D is on AB. So let's say D is here. And I'm given that E is on BC. That's what lies on the interior of means, if you didn't know. So E. And I'm also given that, so this is D, so that AC is congruent to CD, and that DE is congruent to EB. Is that right? So, yeah. And since I'm given the ratio of these lengths, I can, and the answer is also ratio, I can really just assume lengths. So for the sake of simplicity, let AC be 4 and let DE be 3. So I'm given that AC is 4 and DE is 3. So that means that EB is 3 and CD is also 4. Notice that that angle B here, this angle, is equivalent to this angle, right? And that angle A is also equivalent to CDA because that's like a property of isosceles triangles. So I have these two angles here, and I know this angle plus this angle equals 90 degrees because of the big triangle. And this is 90 degrees, so I know the sum of this angle and this angle are both 90 degrees, or is, yeah, 90 degrees. And so because I have a line and this is that one of the angles, and this is the other angle, and I know the sum is 90, and I know that this, because it's a straight line, that the sum of the degree measures of this should be 180, and of these two add up to 90, this must be right. So I know that CDE is right. I'll draw a new diagram, knowing that it is right. So now that is right. This is 4, 4, 3, 3. And what triangle have we been using for our examples? 3, 4, 5 triangles. So like, and because this is right, I can use Pythagorean theorem to find this is 5. But the question asks for AD, this 8 this length divided, or the ratio of AD to DB. So because of the bigger triangle, I get that I can just draw a separate triangle. 4, 5 plus 3 is 8. So I know this is 4 root 5. So I know equals AB. I can drop the altitude here, or I'll erase some stuff. I can draw the altitude here, and because of the altitude formula that was also previously shown, you can use similar triangles to find that this is 12 or 12 over 5. And notice that if I call this F, DFB, because this is right angle, it's an altitude, DFB is similar to ACB. And because of that, I can use ratios to find that, well, I can use ratios again to show that FE, this part, is 9 over 5. And this is 9 over 5, and this will be 16 over 5. So I have a triangle that 3 plus 9 over 5 is 24 over 5. And the height is 12 over 5, right? And the whole thing is like this. This is one of our lengths that we want. We can use ratios or similar triangles to see that if I call this x, I know that 4 divided by 12 over 5 equals 4 root 5 over x. And from this, you can solve to get that 4x. After cross multiplying, you get that, or the 4 goes away because there's also a 4 here. X equals 12 root 5 over 5. Yeah, so you get x is this. And probably going to clear my screen again. So, but that is this part, this dB. So dB, I know this part was 12 root 5 over 5 through similar triangles. Right. And because I know the whole AB, if AB is AD plus DB, and I know AB is 4 root 5, and I know AD, I don't know AD actually, I know DB is 12 root 5 over 5. I know AD. And you can solve this for AD. AD equals, and so you now know that is 8 root 5 to 12 root 5. In other words, this is equivalent to 2 to 3. So yeah, that's how you do this problem.
All right, on to the next problem, which is the 2018 problem 16. Right triangle ABC has leg lengths AB equals 20 and BC equals 21. Including AB and BC, how many line segments with integer length can be drawn from vertex B to a point on hypotenuse AC? All right, now that I have a few answers, I'll go ahead and explain. So what we're trying to find is the number of line segments with integer length from vertex B to AC. I'll draw a diagram to go with it. So we have a triangle. It almost looks isosceles. This is 20, this is 21, and B is the right angle here. So like my hint says, we know that this is a 20, 21, 29 right triangle. It's a Pythagorean triple we memorize. And we know that the shortest line segment we can draw from B to AC is perpendicular to AC. So it's the third height. And we know that 29 times this height would equal 20 times 21. So the height equals 420 divided by 29. And after you do division, it is around 14, but a little over 14. So we know that the shortest integer line segment we draw probably looks like this, and it has length 15. So we know that from the height to the 21 side, we can draw a 15, a 16, a 17, an 18, a 19, a 20, and a 21. That's 7 segments in total. And towards the 20 side, we can draw a 15, a 16, a 17, an 18, a 19, and a 20, because we can draw any length between the height and the legs on both sides. So the answer would be 6 plus 7 equals 13. Most of you got it right, so good job. Now we're working on 2019 problem 10. Wait, 2021 problem 15. This one's very recent.
Okay, I guess I'll present now. Can you lower the screen so I have a bit of, or remove the annotations? Let's see. Okay, thank you. So isosceles triangle ABC has AB, AB, so I know A, C, root 6, right? And a circle with radius 5 root 2 is tangent to line AB at B and to line AC at C. So that means it's like this. And this is 5 root 2. And because it's tangent, I know these are right. So what is the area of the circle that passes through? So I'm finding the circumradius of this, right? Yeah, that's right. So the diagram is a bit weird. And okay, I'll redraw it so it looks better. So I know this is isosceles, and I'm trying to find the area of that circle, and I'm given that a circle with radius 5 root 2 touches B and is also has C. So if I pull out this A, B, C, and let's call the center of this circle O. If I pull out A, B, O, C from here, I get this. And since I know these are right, and I can draw the line, because of SAS, these are congruent, and I can find the length of this rate of this line, which is AO. AO, by the Pythagorean theorem, is 3 root 6 squared, which I'll write this down. 3 root 6 squared plus 5 root 2 squared square root. That's what I'm trying to find for this length. And this length, because 3, so 9, 54 plus 50. So this is, yeah, square root 104. In other words, 2 root 26. And then you have to notice, so, okay, I know AO. Now what do I need to find A to this point. In other words, that'll be the diameter because I know these are right. And yeah, so wait, yeah. I use similar triangles. Wait, yeah. I use similar triangles here. And from not there, here. It's a bit off. This triangle and the big triangle. So if I pull that out, it'll look like this. How about drawing this right? But this is 90, and this is 90. And I know this is the radius. This is this length. This is 5 root 2. And I know that the entire thing is 3 root 6. Well, you could solve this using cyclic quadrilaterals, because you immediately get that this A, C, B, and the point where it touches the circumcircle is cyclic because obviously it's four points on the line, and then you know that because of similarity, a to this point is the diameter of this. So, and because you can use cyclic quadrilaterals again, just A, C, O, B, and then you get, because it's a cyclic quadrilateral, O to this point is a half of AO. So then you get that, wait, yeah. So then it's root 26. So this is our radius of our new circle, I guess. And if we want to find the area, it'll just be that squared times pi. So we have 26 pi. I'll do it a different way because we didn't really do cyclic quadrilaterals, and it's not very, I guess, smart to use those. So you could use trig on this question. You can also use there's a way you use similar triangles, I think. So I'll draw it like this. And I know that, say O, 5√2, 5√2. And I know that this is 3√6, and same thing here. And I will know that I'm trying to find the circumradius of the circumradius of ABC. So I can denote this as R, and I can I can denote this as R, and I can drop the perpendicular here. And well, if I should not probably denote this. What's the letter? I'll just use I. Have I used I? No, I have not. So if this point I is the circumcenter, and I know that A to if I call this point D, I know that wait, yeah, ADO similar to AIB, or yeah, AIB, because of they both share this angle and they both have a tangent. Wait, no, they both have another angle. Draw this. Because these two angles are inscribed angles, they're equal. So because of angle similarity, they're equal. And I know that AD, or no, that's not. AD over AB equals DO over BI. And this means that 1/2, because AD, or because it's the center, because I is the center, this must be the perpendicular bisector, so I know it's half AD over AB. And I know that DO is, I guess, the radius of, wait, DO is the radius, and then I know that BI, this length, is 5√2. I get that, or no, I should write this as DO. DO equals 5√2 over 2. and I also know that AD 3 root 6 over 2 because it's you can use the same logic using the perpendicular bisector. And so basically you have these two numbers and 3 root 6 over 2. And these are the side lengths or the legs of a right angle triangle. Or yeah, and because I've already shown that because it's similar to 3 root 6, 5 root 2. I know this was 2 root 26, and this is just half. So this side length will also be half. So it'll be root 26. So that's our radius, and then you get 26 pi. So it's just a similar argument. Yeah.
All right. Now we're working on 2017 problem 19. Let ABC be an equilateral triangle. Extend side AB beyond B to a point B prime so that the segment B prime is 3 times side AB. Similarly, extend side BC beyond C to a point C prime so that CC prime equals 3 times BC, and extend side CA to a point A beyond A prime so that AA is 3 times CA. What is the ratio of the area of triangle A prime, B prime, C prime to the area of ABC? While I'll finish up setting up my diagram, I'm going to explain. So like Eric said earlier, this problem is all about ratios. So we can just assume that AB equals BC equals AC equals 1. So around this triangle, we're going to draw ones, which means that A prime, B prime, and C prime will all equal 3. So there's two ways to do this problem from here. First, we can find the area of A, B, C using any of the formulas. And then we can find 3 times the area of B prime, B prime, C prime, which is this big triangle I'm going over right now. And these 3 big triangles are all congruent. So we multiply that by 3, and then we put the area of ABC over this. That requires law of cosines with 60 degrees and 120 degrees. And I'll leave that for you to figure out. The solution I like better does not require trig. So we're trying to solve this with ratios. So let's say that the area of ABC is 1s, because usually we use s for area. We're trying to figure out how much s the B prime C prime triangle is. So I know that if this is ABC, this is 1, this is A, B, we extend B all the way to B prime, and B prime is C. So let's just pretend that B prime C it's just B prime and C, not C prime, so it's not as big. So can anyone tell me the ratio between ABC and BC B prime? And my hint here is that they have the same height. I'm getting a few answers already, so I'll go ahead and explain this sub-problem. So we know that they share the same height, but they have different base lengths. The area of ABC, according to this so far, is h over 2, while the area of B prime C is 3h over 2. So the ratio of this in terms of s would be 3s. Now we're going to turn this into the actual problem where we extend C to the C prime. And we know that this is 1, this is 3. So now we know that B prime C also has a different height, but we don't know what the height is. We can also use ratios like we did earlier to figure out, because the ratio of AC to AC prime is 1 over 4. The ratio of the heights is also 1 over 4. So this is 4h. If you didn't understand, this was similar reasoning to the earlier subproblem where we were trying to find the ratio of areas. But now the ratio of the bases and heights are different. So we multiply the 3 and the 4. So each of these big triangles is 12s. So 12s multiplied by 3 is 36x, and 36 plus 1 is 37. So eventually we're going to get s divided by 37s, and the ratio is 1 over 37. I think I was a bit fast on that. Does anyone have questions about how I found the ratio of areas based on the side length ratios? Yeah, just like Eric said in the chat, we are about to end and we don't have time for another problem. So if any of you want me to explain how I did this problem again, or if you would like practice with this types of skills, please let me know. I don't think there's time for another problem, but if you want to look at one, sure. There's the 2017 problem 21. And my main hint is that with my hint, this is going to be really quick. You can see that this is a 6, 8, 10, which is another version of a 3, 4, 5. And D is the midpoint of BC, and we talked about medians earlier. So we know that AD is median. The special thing about right triangles is that the median is equal to half of the hypotenuse, the median to the hypotenuse. So AD is also equal to 5, as you can tell. And going from here, we can use the in-circle formula.
Okay, so I'll finish this one and then we'll be pretty much done. Well, yeah, we'll be there. So the first, this triangle, AB. This is our I'll do ABD first. Notice that it's 5, 5, and 6. So if I drop the altitude, this will become 3 because I know this is isosceles. This will be perpendicular bisector. I know this will be 4 by Pythagorean theorem. And so I know the area, and I know that the semi-perimeter is 8. So I know that that radius is 3 over 2. And I have to add it on to the other one. The other triangle is a If I do the same thing here, I get that it's 5, 4, 4, 5, and I get the height is 3. So I know the area is also 12, but this time the same perimeter is 9. So I know my radius for this one will be 4 over 3. So 4 over 3 plus 3 over 2 equals, so 8 plus 9, 17 over 6 is your answer.